I'm discussing chapter 14, Kinetics of a Particle, Work and Energy. And the first paragraph out of the 18 pages of theoretical development in the chapter by itself is almost 60 pages. It's about the work of a force. The work of a force is a scalar. And if you look at a particle that's moving on a curvilinear path, we have a position vector as a fixed point r, and a moment later, infinitesimal moment later, dt, we have a new position vector r prime. The change in r, there will be r prime minus r is dr, and it's shown here as a vector. And the force vector in general makes an angle theta with dr vector. And we define the work, infinitesimal work of this force F as it moves between corresponding position vector r and r prime as F ds cosine theta. ds approximates dr for small increases of small displacement, that is small time intervals. So we can write, instead of using cosine theta, we can use the dot product to define the infinitesimal work du. Okay, and the maximum effect that the force can have in terms of work produced is when this angle is 0, that is cosine is 1. It is zero effect when the angle is pi over 2 or 90 degrees, and it's a negative past 90 degrees and has the maximum negative value, that is the maximum or is the minimum for theta being 180 degrees, that is force opposes motion. It's against the motion of the particle for an angle equals to 180 or pi degrees. Now the finite amount of work between two positions, we have position vector r1 and position vector r2 for a second position, is defined as an integral going from r1 to r2 of this f dot dr, or from s1 to s2, and you can see here cosine theta ds. If we're to plot this function f cosine theta, the work between s1 and s2 is the area under the curve, f cosine theta. Work of a constant for moving on along a straight line. So if in particular the path of the particle is rectilinear, and if the angle is constant, if the force is constant, then the work done between position S1 and S2 is going to be the projection of the force along the direction of displacement of the particle times S2 minus S1. Graphically, so this graph becomes a rectangle. Again, this is constant, and it explains this this form here. Weight is the force that the gravitational field of the Earth acts upon particles, and there we have, so this is a graph, and it shows the y-axis is the vertical axis, and weight, it's always going to point downwards and be parallel with the y-axis. So if we take the definition of work and explicit the dot product by using the components of the displacement dxi, dyi, dzk, I, j, and k are the unit vector associated with the positive direction of the x, y, and z axis, then we get the work of gravity, or work of weight, as being negative weight of the particle times the change in height, dy. So it would be only the difference in elevation in y coordinate that is involved in this equation. So later on we'll discuss conservative forces where the work depends only on the initial and final positions and not the shape of the path in between the two positions. And this is weight or gravity produces conservative forces. Weight are conservative forces, same as the spring forces, but that will be for a little bit later. So what is the work of a spring? You have an ideal spring is we're assuming massless of rate k, and your say the particle is connected to the spring, and you apply a force towards either compressing or stretching the spring. And depending on how you measure S, and we assume identical behavior in tension and compression of the spring, so the work done by the elastic force of the spring is going to be the this integral, and the spring force is we know it's Ks, and there's a minus because as the spring gets either stretched or compressed, there is an opposing force. So we're talking that spring force rather than the force that has to be applied in order to unilateral action and reaction. So this is just showing a force, but there is a force coming from the spring and vice versa, from the particle to the spring, from the spring to the particle. Anyway, so the work done by compressing or stretching the spring between positions 1 and 2 has this formula. So there is a negative in front, final position 1 over 2 ks squared, again coming from integrating, since force is linear with the spring deflection, and negative 1 over 2 ks1 squared, the initial position that corresponds to s1. Graphically, spring force ks, it's a line through the origin, and the work done between s1 and s2 is the area of the trapezoid. Okay, and in terms of the sign, I said earlier that you can either compress a spring or you can stretch it over its unstretched position, and we need to measure the deflection S from the unstretched position in order for this equation to hold true on one hand. And then in terms of the sign, if you're working against the spring, the work done between the two positions would be negative. If you work with the spring, essentially relieving of the compression of the stretch of the spring, then the work is positive. Okay, so if you work against the spring, either further compressing it or further stretching it, the work would be a negative value. Okay. We have this principle of work and energy, which is an integral form of Newton's second law. So you know Newton's second law as sum of forces equals mass times acceleration, and this is stated for the normal tangential coordinates, is stated in the tangential direction. Forces that act in the normal direction do not produce work, because there's no change of s in the direction perpendicular to the tangent, to the curve, to the path of the particle. Okay, and we take Newton's second law written in the tangential direction, and we are going to use this form of the acceleration. That is, acceleration is dv over dt, but we change it to v times dv over ds. And if we put it in, if we integrate between two positions, S1 and S2, then we have on the left hand side the work of the forces that act upon the particle, and we know now that's only the tangential component that produces work. And then on to the right we end up with this difference, 1 over 2 mv2 squared, so final velocity squared times mass taken half, and then 1 over 2 mv1 squared, so this is initial velocity squared times mass taken or divided by 2. Okay, and this, we call this kinetic energy. So 1 over 2 mv is kinetic energy. So a particle in motion, particle of mass m in motion of velocity v1 carries kinetic energy, which by slowing the particle is released. Depends on how you do this slowing down, but that can say multiple particle, like a stream of sand particles hitting a blade of a rotor, and that rotor rotates. So there's work produced by slowing the particles. Okay, a form that is used in applications for the principle of work and energy is this one. You're looking at initial kinetic energy plus the work done between initial and final position between position 1 and position 2 equals the final kinetic energy. And these are, again, this is an integral form of Newton's second law, and it can be used when we have force velocity displacement between two positions. So there's no time involved here. It's just this. It's just the displacement that's the independent variable. Okay, and summary of the pages discussed so far. How do you procedure for analysis? And it's listed here. You do the free body diagram. You account for all the forces acting upon the body. You define the reference from where we measure displacement. You state the work energy, the principle, and knowledge about the initial velocity and the work done allows you to calculate final velocity, or knowledge about the initial and final velocities allows you to calculate the work done in upon the particle between instance 1 and instance 2. Okay. And yeah, and in case of gravity, work would be W times displacement, vertical displacement y, and if the particle lowers its elevation, it will be a positive work. If the particle increases its elevation, it's the negative work. That's why the minus sign in an early equation. In the case of a spring, the work of a spring is 1 over 2k times deflection squared, and deflection is measured from the unstretched shape or position of the spring there. If we have systems of particles like you see them here, and you have forces acting upon some or all of the particles, and you have internal forces between particles, you can state the work and energy equation, where you have kinetic energy initial of the entire collection of particles, kinetic energy of the final collection of particles, and the work done between 1 and 2 upon the system. And if there's, of course, between the particles, there can or could be interaction, and they always act in pair, action and reaction. And if there's no change of distance between the particles, like if this is a model of a rigid body is made of many particles, then the internal work or work of the internal forces rather is it's 0. So it will be here, the second term will just be the work of the external forces. Okay, work of friction caused by sliding. Very common example where you have or as we know, friction force opposes motion. We have here a free body diagram of this block that's sliding on horizontal surface. We have the weight acting. There is normal force from the surface upon the block, and then we have friction opposing motion. P, the external force, is shown here in the direction of sliding, direction of S. If we state the principle of work and energy, we have initial kinetic energy, and this is the work of force P. Okay, P is assumed constant, so it will be P times displacement S. And then the work of the friction force. We know friction force is kinetic coefficient of friction times normal force, which is equal to W. There's no work done in the vertical direction. Path is rectilinear and horizontal. So the work of the friction force is going to be negative because positive is to the right and displacement is to the right. So friction force opposing motion is to the left, so negative. Equals kinetic energy at the second position. All right. And the work of the friction force is going to always be negative and always opposing motion. It's the result of having friction force present and displacement happening. There is relative motion between the two surfaces. This heat generated, but also you have change in the structure of the surfaces. So say this is an abrasive block and this is a piece of wood. As you slide it, you're going to produce sand dust and scratches, and so that's a change in the structure of the surface. That's an increase in from other class from thermodynamics, increase in entropy. Okay, so the work of friction is irreversible. It's always going to be negative, subtracting from the kinetic energy. And clearly, if we move back and forth this block against sliding the abrasive block against the wood block surface, like I said, will continue to produce heat and produce sawdust. All right, another section, power and efficiency. So we define power as a time rate of producing work by machines, by people, by work animals. And we define power as the change in work over the time that change of work it's produced. So you can have a two cars, one small automobile and a big one, and the result or the difference between the two is that one has a more powerful engine and will be able to accelerate faster. That's one ability of a more powerful engine. The other one is that the more powerful engine, or the automobile with the more powerful engine, will be able to tow a trailer or carry more load on an incline faster. I said more. There's limitation. I mean, we need to go into details like how transmission is designed and such, but you recognize from or know from everyday life experience. So a less powerful truck will have to go slower at the same amount of loading of the more powerful one on the same grade slope road, that is. Okay, so moving forward, we explicit the work part du using the dot product And then by rearranging terms, we get force, vector force, dotted with the velocity vector. dr over dt is the velocity vector. Okay, so we can also write power as dot product between force and velocity. Okay. And we'll come back to a discussion about power. There's power in rotational motion. Think of rotating wheels in the crankshaft of the engine rotating. Of course, transmission and the fact that wheels are in contact with the straight rails turn it into a rectilinear motion, but it starts with a circular motion. And we'll discuss power and circular motion later. Efficiency. So efficiency is the ratio between the output power and the input power. Okay, so you have the there's losses. You have the engine, you have the crank rotating, and the engine power is delivered to the wheels, and through measurements we can assess the rotation power of the engine, but that will be more than the power that is done by moving the weight of the engine and the rest of the train up a grade. Okay, so input power over output, or the output power over input power, is always going to be less than 1, ideally 1, but never greater than 1. We can also define efficiency as the energy output over energy input, or it could be work, energy and work. Work of a force, the work done by, say, have a lever, and somebody acts upon one end and with a fulcrum, and you have a short displacement working against a larger force. They could be losses, and they are at the fulcrum. There you have contact and rubbing and friction happening that was possible deformation. So the work of the person acting upon the long length of the lever and the work done by lifting the weight, you take the ratio inverse to the way I stated earlier moments ago, and it gets you the efficiency of that lever. Of course, that's a simplistic case, but you have transmissions. You have, we discussed engine, the diesel engine of this locomotive, and there's the transmission and a torque converter and all that. So efficiency would be due to the losses that's happening and all that, a chain of components that interact. Okay. All right, so here's summarized procedure of analysis for the power and work and efficiency analysis. And you recognize the forces, and then the information about whether the body is accelerating or not accelerating, and you're determine the velocity of various instances, initial and final velocity, and you state the power as the work done by divided by the time interval that work is produced. Okay. So essentially, power, more powerful, contrary to some the understanding of some people. So a powerful person, you think of being able to develop large forces, being able to lift a heavy weight. But in dynamics, power is a measure of how fast work is done. So yeah, the more physically fit person could do faster, lift faster, say 20-pound weight, than say a short or a young person and a child. And it's it's like I said, it's not about force capability, or rather ability to do work, larger amount of work in the same time interval. All right, section 14.5. This is on conservative forces and potential energy. Okay, so the conservative forces are those that we discussed two so far. There's the gravitational force, and there are the elastic spring forces. Those are called conservative because the work done depends only on the final initial position. Okay, so if you're moving a particle of mass m or weight w between, you start from position 1 and move up and reverse and come back, and as you reverse motion and reduce the height of the particle, which is measured from, you need to choose a datum, a reference horizontal plane or line. So as you reverse motion going with gravity, there is work created. As you move up, increase elevation, the work is negative. So the work of gravity ultimately depends only in the initial and final position. But you need to choose a datum and refer to it. You can go below it. Y will become negative. No problem with that. Usually for convenience, we choose the datum like the lowest elevation that the particle could reach. Okay, like yes, of this grain, you choose the ground surface. If you maneuver weights inside of or if this is on a, sometimes you see them installed on top of buildings that are under construction. But you choose the datum at the ground level. Okay, if you manipulate weights inside of a pit, you choose the datum at the bottom of the pit for convenience, but it's not necessary. Anyway, so in case of we discussed energy, we discussed kinetic energy. So kinetic energy is a measure of the particle's ability to do work by virtue of its motion. You can have chemical energy. You have a particle that is some reactants, and it can produce energy by particle like a block of charcoal produces energy by burning. No, we're talking about energy due to the presence of motion, or the motion of the particle. Okay, so gravitational potential is a scalar function that we define it as weight times elevation measured from a datum. Okay, so this is the gravitational potential. In case of a spring, we are limited in choosing the datum. It has to be at the unstretched position of the spring. Could have an extension, but you choose it to where the spring is unstretched, uncompressed for that position. And the elastic potential is going to be 1/2 ks squared. And being squared, doesn't matter whether you compress or stretch the spring. That says with the weight, say you stretch the spring and you come back and you unstretch it some and you stretch it again, and ends somewhere, could be back to where it's unstretched or otherwise. But as you move towards further increasing the stretch, and you undo partially that stretch, that's work that's recovered, and it matters only the initial and the final position when it comes to evaluating the work done by the elastic spring. And again, the work of the elastic spring is going to be a negative one if you work against the spring, and it's a positive one if you work with the spring. That is, you undo of its deflection. And deflection could be stretch or compression. Okay. Anyway, so in case of elastic springs, this is the equation for elastic potential, and you will have it's position bound. It depends on the position, both same as with the gravitational potential. Now we can define what's called a potential function in systems where there's both gravitational potential and elastic spring potential. And by the way, there are other conservative forces than gravity and elastic springs. There are electric fields, magnetic fields. They have potential, and if you can maintain a constant force and a constant direction like gravitational forces are, could talk about the potential of a force that maintains direction and it's constant in magnitude, say. So mimicking the weight, or could mimic the elastic force. And so our forces like electromagnetic force depends on their function of distance. They decrease with distance. And for very large displacements in gravitational field of the Earth, of the planets, you have a change in weight, but that field remains I'm using the word conservative. That will be discussed in just a little bit. Anyway, so potential function V, it's gravitational potential, elastic potential, and the work done between two instances of the particle, or systems of particles saw it earlier. So the work between 1 and 2 instances or positions, it's going to be the difference between the potential function at the beginning and at the end. Okay, so we can explicit what the gravitational and elastic potentials are, and then write them for position 1 and position 2. You see these two, and rearranging terms, we get weight times final minus initial position, and then we get for the elastic potential, could even factor 1 over 2 times k, and this is but in any case this would be corresponding to the elastic potential term, and emphasizing again that the datum has to be from the unstretched spring position. Now some developments here. So if we look at the infinitesimal work and infinitesimal change in potential function, then and using x, y, and z Cartesian coordinates, we get the small infinitesimal change of work as the infinitesimal change of the potential function, and then expliciting what the work is, force times small displacement dr. Okay, and this is the dot product between two vectors. Okay, and applying dot product, and so what is next is taking this du, and we write it as so using this result, okay, in this fashion. And in order for this to hold, we need to equate terms. So this has to be this part, Fy has to be this part, Fz has to be this part. Okay. And it says the change in x, y, and z are independent of each other only if we have these three equation holding. And we can write moving between what was originally here, we can write that the force vector is what is called the negative gradient of the total or the potential function. Okay, this is the nabla operator, and what it says here. So you take the scalar field of the potential function, and the gradient of it would be the force F. Um, in case of the gravitational potential, the we chose the y-axis, the z-axis. Okay, so it means that this term is 0, this term is 0, and weight would be the fy function. But in any case, you start with the potential function, and the conservative force to that potential function is going to be the negative gradient of that scalar. Okay. So you have a scalar field, and the force vector is the gradient of that scalar field. All right, conservation of energy. In mechanical or particles, one particle, systems of particles, we can extend it to systems of particles. You're looking at this formulation. So you have initial kinetic energy, you have the initial value of the potential function. There is the work of the non-conservative forces. They have some friction going on, and then this is equal to the kinetic energy the second instant and the value of the potential function at that second instant. And again, or if there's work done by non-conservative forces, you would expect or clearly just the kinetic energy and the potential function, initial and final, to differ. But otherwise, if this component is zero, negligible, we can write kinetic energy, potential at the initial position equals kinetic energy and potential total elastic and gravitational potential at the final position. Okay, and this is conservation of mechanical energy, or conservation in energy. And it's you can have a exchange of between kinetic and potential energy, but the balance of the sum of the two, kinetic energy and potential energy, remains unchanged if we don't have non-conservative forces acting. And they give the example here of a ball that drops. So it starts from 0 at some elevation, and as it moves down, the potential energy is decreased, and we have an increase in kinetic energy. And we know how to calculate the velocity of a falling particle, and we can actually solve quicker certain type of problems with falling particles, with particle moving in gravitational field, or against elastic springs. Or you can have a spring hanging vertically with a particle at the end. But again, it simplifies. You use directly the integral form, this conservation of energy principle that allows you to calculate say final velocity given initial velocity, and include or making use of the potential energy, which is changing as the particle moves along the gravitational field. And for systems of particles, although the chapter says work of an energy of a particle, the systems of particles will be sum of kinetic energy, sum of potentials, initially and finally. And if there is no conservative forces or non-conservative forces, there is no loss of energy, then the two are equal. Okay, and here's the procedure of analysis, essential to choose the datum for elastic springs, the non-deflected spring, for motion or or particle system of particle in a gravitational field, you choose it preferably at the lowermost position, and stay the conservation of energy. Okay, and yeah, there are a couple of pages of chapter review where you can go and look for what equations to use, which aren't many, by the way. So there will be really would be just knowledge of what kinetic energy is, which I'm sure you know from other classes, and then for conservative systems where there's no loss of energy, you stay the conservation of energy equation, and you could use it equally well, the work energy equation, when you have, what was it, what was the other page, where you have dissipative work, like the work of non-conservative forces we discussed. Anyway, 41 minutes of recording. I'm going to post this, and we'll spend face-to-face time solving problems. Thank you for watching.